Today we're going to look at a Putnam problem from 2021, specifically problem A1. Like many of the easier Putnam problems, this is going to be the type of problem where we can use intuition or investigation of simple cases to guess the optimal solution, and then we prove the solution is optimal using some auxiliary object or quantity defined from the objects that feature in our problem. Today's problem says that we have a grasshopper placed at the origin who wants to reach the point 2021-2021 by hopping in hops of length 5, with the restriction that the grasshopper can only go to points with integer coordinates. We want to find the least number of hops required to reach 2021-2021. Feel free to pause the video and figure this one out yourself, and then we'll go over a solution to this problem. The first thing to do to solve this problem is to draw what the allowable hops look like so we can use visual intuition. We get the following graph. Notice that the point we want to reach is in the 1-1 direction, or along the line y equals x. If we take a 0-5 hop and then a 5-0 hop, we end up traveling to the point 5-5 in 2 hops. But if we take a 3-4 and then a 4-3 hop, we get to the point 7-7 in 2 hops. It seems like alternating 3-4 and 4-3 is going to be the fastest way to get to 2021-2021, because the vectors for those hops are closest to the direction we need to go. So let's assume this is our solution. How many hops does it require to get to 2021-2021? Well, we know in 2 hops we can get to the point 7-7. If we divide 2021 by 7, we get 288 with a remainder of 5. Because the remainder is non-zero, we will not be able to make it to 2021-2021 by only alternating between these 2 hops. However, we can get to the point 2016-2016 in 288 times 2 hops, or 576 hops. And then we can take a 5-0 hop and a 0-5 hop, making for a total of 578 hops. This seems like it should be the fastest way to get to 2021-2021. The last thing to do to have a solution for this problem, and usually the hardest part of these kinds of problems, is to prove this is an optimal solution. That is, prove that there can be no solution with fewer than 578 hops. To do that, we're going to define an auxiliary quantity. It's a quantity that can be built from the objects we're dealing with in the problem, which in our case are points in the Cartesian plane. Points in the Cartesian plane have x and y coordinates. So one possible quantity that we can make use of is the sum of coordinates quantity. Let's think about this problem from that perspective now. The point we want to reach has a coordinate sum of 4042, and the hops we're allowed to take each change our coordinate sum by plus or minus 5 or plus or minus 7. In terms of this new quantity, a solution to our problem requires that we change our starting coordinate sum of 0 at the origin to the destination coordinate sum of 4042. And the hops we're allowed to take allow us to increase our sum by at most 7. 4042 divided by 7 gives us 577 with a remainder of 3. This means there cannot be a solution with exactly 577, nor with fewer than 577 steps. Therefore, our solution with 578 steps is optimal. That's all for this video. Thanks for watching.